Hello everyone. This is the third video under linear transformation. In this video, I'm explaining matrix of change of bases. So initially, I had taken the transformation rotating a plane by 90 degrees. So it is t of x comma y equal to y comma minus x. This is how the transformation is represented algebraically, where we are rotating a plane by 90-degree clockwise. Okay, and matrix of this linear transformation, matrix of T is given by A equal to where the standard basis vectors with respect to standard basis I am talking, matrix of T with respect to standard basis is given by 0 minus 1, I cap goes to the new position 0 minus 1 and j cap goes to the position 1 0. Okay, this we had seen in the last video. Now we want to know about matrix of change of basis, because when you change the basis, matrix of the transformation also changes. That you have seen in the previous video how it changes. Means when you change the basis, the representation of points in a plane also changes. So R square, you know, that is a vector space. It is a vector space over the field of reals. R square is the thing, but it is a plane. Plane is not having any intrinsic coordinate system. What basis we choose, based on that we are taking the coordinate system. If we choose the standard basis 1001, then accordingly we have the standard coordinate system. So if you change the basis, then with respect to the basis vectors, scaling and adding those basis vectors gives you the new position of the vector in a plane. Means every vector in a plane can be written as a linear combination of basis vectors in different way. So suppose if you take S is equal to 1 0 and 0 comma 1, this as the basis, that is standard basis, and S dash is equal to, I'll take 1 comma 2 and 2 comma 1, these vectors. This is another basis. When you consider this as a basis, every vector in R square is a linear combination of 1 0 and 0 1. When you take S dash, every vector is a linear combination of 1 comma 2 and 2 comma 1. A linear combination in the sense, scale these vectors and go to the required position. Okay. Position remains same in both the cases, but their representation changes. In terms of S representation is different, in terms of S dash representation is different. So before knowing what is matrix of change of basis, first let us understand what is coordinates of a point. Okay, coordinates, or else we can say coordinate vector. Coordinate vector. See, for example, when you consider any point as x comma y, okay, now this x comma y in terms of 1 comma 0, that is p into 1 comma 0 plus q into 0 comma 1. With respect to the basis, if we have chosen s as the basis, x comma y can be written as a linear combination of these basis vectors. So p equal to x and q equal to y. When you solve that, means coordinates of x comma y are nothing but x comma y. That is because with respect to the standard basis. Suppose if you have chosen basis s dash, then coordinates of x comma y, take any vector x comma y, then it should be written as a linear combination of 1 comma 2 and 2 comma 1. Then you have to solve this system. So after solving this, you will get P equal to 2B minus A by 3 and Q equal to 2A minus B by 3. Okay, that is if you have taken this as A comma B. So any vector V, this is in terms of the usual coordinate system. This is called a standard coordinate system, and most of the time we are using the standard coordinate system itself, a rectangular coordinate system. Okay. So now A comma B is any vector in terms of standard coordinate system. When you take some other basis other than the standard basis, then every vector with respect to that basis has coordinates of the form 2b minus A by 3 and 2a minus B by 3. That means if V is your vector, with respect to s dash, the coordinates of v with respect to s dash is given by 2b minus a by 3 and 2a minus b by 3. So this vector is called as a coordinate vector of v with respect to basis s dash. Similarly, you may have n number of bases for r square. When you go on changing the bases, you will get different coordinate vectors for the given vector. Given vector v is in terms of our standard coordinate system. So you have to write that vector as a linear combination of given basis vectors. Then you will get those p and q values. That gives you coordinate vector of v with respect to basis s dash. That means this gives you a standard coordinate system. This gives you a new coordinate system where the same vector v with coordinates a and b is called like this. That is how to represent the vector under the basis s dash. Let us illustrate this. Yes. Now look here, this is standard coordinate system where this is I cap and this is j cap. Every other vector in the plane is a linear combination of I cap and j cap. That means if you want to go to the position 2, 2, that is this position here, 2, 2 is this position, that is 2 times I cap and 2 times j cap. Add those two vectors to get the new position 2, 2, that is 2, 2 is 2 times I cap plus 2 times j cap. That is, here scale this vector and scale this vector also. This is the new position. Now you can't add like this. Use the triangle law of addition. So bring this vector here, tail to head. Okay, it comes here. Now the resultant, third side. This vector represents 2, 2. That is how to go to any position in R square using the standard basis. Now I had given you a new basis 1, 2 and 2, 1. Now this new basis is coordinates are in terms of our standard basis. So as per, you just imagine the background as a standard basis. As per that 1, 2 where it comes, this is origin. So 1, 2 comes here and 2, 1. I have not marked here y-axis and x-axis specifically. That is because now this is a new coordinate system where these two vectors act as a basis. So every other position is reached as a linear combination of these vectors. So any vector, now these are in terms of standard coordinate. In this new system 1, 2 is called as and 2, 1 called as. That means I need to get the coordinates of 1, 2 and coordinates of 2, 1. Look here, that this is how to do. You know, any vector with respect to s dash is represented as 2b minus a by 3 and 2a minus b by 3. This is how just now we found. Now the vector is 1, 2. 1, 2 is in our language. You think that there is our language and this is somebody else's language. You just imagine this is some alien's language and that was our language, standard coordinate system. Now we want to convert the information shared between these two systems. So that is 1, 2 is in our language. It is called as, put b equal to 2 here. 2 to the 4 minus 1. 4 minus 1 is 3 by 3 is 1. Then 2 minus 2, 0. 1, 0. Look here. 1, 0 usually our standard basis. The same vector is called as 1, 0 in this language. Similarly, this becomes 0, 1. Means to reach this position, okay, it is scaling 1 times 1, 2 and 0 times 2, 1. Then we reach the position 1, 2. Okay, here also 0 times 1, 2 and 1 times 2, 1. Then we will get the coordinates of this vector 0, 1. So in this alien language it is called as 1, 0. In our language the same vector is called as 1, 2. Means position is of 1, 2, but in that language it is called as 1, 0. In our language it is called as 1, 2. So coordinates of 1, 2, 1, 0. Similarly, look here, suppose if you take minus 2, 2. This is in our language minus 2 comma 2. So in this new language minus 2 comma 2 is called as 2 minus 2. Coordinates of minus 2 comma 2 with respect to the basis s dash is 2 comma minus 2. So first plot where comes minus 2 comma 2. So this is minus 1 minus 2 and 2 1 2, that is this position. So this position gives you minus 2 comma 2 as per our coordinate system. This is minus 2 comma 2 as per our coordinate system. Now as per the new coordinate system, the same vector is position remains same, but the way of telling it changes. It is called as 2 minus 2. That is because 2 times 1 comma 2 plus minus 2 times 2 comma 1. It is scaling these vectors, basis vectors. How to scale these basis vectors? 2 times 1 comma 2. So where comes 2 times 1 comma 2? 2 times 1 comma 2 is nothing but 2 comma 4 at that position. 1 2 and 1 2 3 4, that is here, this position. Yes, this is 2 times 1 comma 2. So scale the vector 1 comma 2 as 2 times 1 comma 2. So you will get here this vector. This is 2 comma 4. Okay. Next minus 2 times 2 comma 1. 2 comma 1 is here. Minus 2 times means length increases by 2 here. Okay, 2 times that of this vector, but direction is opposite because it is minus 2. So this vector, so it comes here, when you multiply it by minus 2, it becomes minus 4 comma minus 2. So where comes minus 4 comma minus 2? That is as per our coordinate system. So it's 1 2 3 4. Okay, this is minus 4, then minus 2 1 2, that is at this position. This position, correct? No, this is how it comes. This vector is minus 4 comma minus 2 as per our language. Now you have to add these two vectors to reach the required position. So how to add these two vectors now? So head to tail. So this same vector you have to bring it here. Okay. See, this comes here. So here, therefore, 2 times 1 comma 2 and minus 2 times 2 comma 1, where finally it reaches the position, same position, minus 2 comma 2. But in the new system, it is called as 2 comma minus 2. Correct? No? When you change the basis once again the representation changes. Same vector, it was minus 2 comma 2. Now it is in this basis, with respect to this basis, it is called as 2 comma minus 2. Hope you understood what is coordinate vector and how to find the coordinate vector for the given vector. So now I have taken S as the standard basis. S can be any other basis as well. So in that case, you have a new system, another new system, means with respect to S and with respect to S dash, you need to communicate between those two systems. So this way of getting the coordinates of a vector is called as finding the coordinates of that given vector. Now I want the matrix of change of basis. Now, matrix of change of basis can also be used to find the coordinates of vectors between the two different systems. See, for example, S is equal to, this is the standard basis, S dash is the new basis, correct? No, this you can call it as old system and this is a new system you call. You know that now? In new system, the coordinates are very much different from that of old system. Now, matrix of change of basis. When you change basis, then there will be definitely change in coordinate systems as well. Okay. So, to get that matrix of change of basis, you know that when you change the basis, matrix of the transformation also changes. So, now to get that matrix of change of basis from S to S dash, I will name that matrix as P. To get that P, first write from S to S dash. So every vector of S dash is, that is 1 comma 2, is written as a linear combination of S, vectors of S, that is x into 1 comma 0 plus y into 0 comma 1. So 2 comma 1 as x into 1 comma 0 or else p into plus q into 0 comma 1. So this is easy as it is standard basis. Xy comes out to be 1 2 and by pq also comes out to be 2 comma 1. So p is equal to, write it as a column, 1 2 and 2 1. So this p is called as matrix of change of basis from S to S dash. Okay, this P you have to remember gives coordinates of V in S dash to coordinates of V in S. So if you have a vector V in S dash which is having its own representation, its own coordinates. Now if you want to calculate what it is called in the old system S, then we have to use P. Though it is from S to S dash, but it gives you the coordinates of V in S dash to V in S, the reverse. This change of basis matrix can also be used to find the coordinates also. Correct. Now, see for example, you take this 2 comma minus 2. So P 1 2 2 1 and you want to know the coordinates of 2 minus 2 in the old system. So 2 minus 2. What this vector 2 minus 2 is called as in the old system. So 2 minus 4, it is minus 2. Then 2 minus 2, 2 2 is a 4, minus 2, it is plus 2. See, look here, same. Correct. Now this is in the old system. So this is in the new system. So this is the matrix P, matrix of change of basis. So if you multiply any vector of S dash by this matrix of change of basis, then you will get what that vector is called in the old system. Say for example, one more vector you take, 1 2 you take. This is the basis vector 1 2. 1 2 2 1. This is in the new system. Okay, in the old system this 1 2 is called as 1 plus 5 4, that is 5. 2 plus 2 4, it is called as 5 4. Similarly, you know that 1 0 is called as 1 2. Correct. 1 2 2 1. The vector 1 0 here, what free vector I use, it is new system. Okay, in the new system you know that 1 0 in the new system is called as 1 2 in the old system. So I should get 1 2 now. Okay, so 1 and 2. See, you are getting same. This is in the old system. So matrix of change of basis gives you the coordinates of a vector which is in S dash to coordinates of a vector in S. It is a matrix of change of basis from S to S dash, but it gives you coordinate vectors of a vector in S dash to vector in S. Okay. Now P inverse, which is nothing but Q, this is called as transition matrix. Transition matrix or matrix of change of basis from S dash to S. Again, you can communicate vice versa. That is, communicate between S dash to S. Then you have to take the inverse of this matrix, that is nothing but Q, which is called as a change of basis matrix from S dash to S or transition matrix from S dash to S. What this Q does is it converts the coordinates of V in the old system to coordinates of V in the new system. Little confusing due to this. From S dash to S means usually we think coordinates of V in S dash to coordinates of V in S, but that is wrong. It's reverse of this. Coordinates of V in the old system is converted to the coordinates of V in the new system by Q. But P, what it does, it converts coordinates of a new system to the coordinates of old system. So if you want to find Q, if you want to find out, you have to write every vector of this as a linear combination of this, which is nothing but finding inverse of P. How to find inverse of P? Change these diagonal elements, change the sign of these two elements, then divided by the determinant 1 minus 4, so minus 1 by 3. Okay, so this gives you minus 1 by 3, 2 by 3, 2 by 3 and minus 1 by 3. So this is the matrix of change of basis from S dash to S. Now if you take any vector of old system, and if you apply this matrix to the left of that vector, you will get the coordinates of that vector in the new system. Let us check. 1 2 in our system is called as 1 0 in the new system. Let us try with that. So here the matrix is minus 1 by 3, 2 by 3, 2 by 3, minus 1 by 3, and here comes 1 2. 1 2 is of old system. 1 2 is called as 1 0 in the new system because that is one of the bases. Let us check. Minus 1 by 3 plus 4 by 3, 3 by 3, 3 by 3 is nothing but 1. Next 2 by 3 minus 2 by 3, which is 0. Look, this is what it is called in the new system. So matrix of change of basis helps you to communicate between two different systems. Those two different systems are arrived due to two different bases. So this is how to get the matrix of change of basis. So consider this transformation: rotating a plane by 90-degree clockwise. With respect to the standard basis, the matrix of this transformation is this, and with respect to any other basis S dash, this basis, the matrix of the transformation is this. Okay, now this matrix of change of basis, why it is necessary? Because so you can write B equal to P inverse A into P, means the matrix of change of basis with respect to any other basis can be written as a product of these matrices, where P is the matrix of change of basis from S to S dash. Okay, see, we got P as 1 2 2 1. Okay, and its inverse P inverse, which is nothing but Q, as minus 1 by 3, 2 by 3, 2 by 3, and minus 1 by 3. Okay, now when you apply that here, A is the matrix of transformation, this transformation with respect to the standard basis, that is 0 minus 1 1 0. Then here comes P 1 2 2 1. Then here comes P inverse minus 1 by 3, 2 by 3, 2 by 3, minus 1 by 3. So this finally gives you minus 4 by 3, minus 5 by 3, 5 by 3, and 4 by 3. That means to communicate between these two systems, this is necessary. So here it is like, if you have a vector, so if you have a vector in this S dash, vector in S dash, we want to find out where it goes to after applying the transformation. For that, what you should do is, first you have to write here change of basis matrix, that is in our system. Change of basis matrix from our system to the new system, S to S dash. Then the matrix of transformation, that is also in our system, that is A. Then P inverse, this is our system. This is also the matrix of transformation with respect to S. P inverse, this is of new system. Then you will get where this vector goes to into the new system. It is same as multiplying this matrix with that vector. So take any vector of a new system. Then for that you have to write the matrix of change of basis from S to S dash. Then you write the matrix of transformation with respect to our system. Still it is in our system only. Then if you multiply with the P inverse, then you will get the coordinates in the new system. So whatever the new matrix you got for the same transformation, this implies that A and B are similar matrices. So this is what the meaning of similar matrices. Similar matrices are nothing but they represent the same linear operator. Operator was T from R square to R square, which is a rotation of a plane by 90-degree clockwise. This matrix as well as this matrix represent the same linear operator, but with respect to two different bases. So all such matrices form a new category called as similar matrices, because they represent the same linear operator. So if you change the basis, one more basis, S double dash, if you take a new basis, then you will get a matrix of this transformation with respect to that basis. Then that matrix is also similar to B as well as this matrix A. So similarly, you can have the concept of diagonalization of matrices. You know that some matrices are diagonalizable and some are not diagonalizable. So diagonalization of matrices is nothing but two matrices are said to be diagonalizable if we write, usually we write like this: P inverse AP equal to a diagonal matrix. If this expression holds, then we say that the matrix A is diagonal. The intuition behind this is that if you have a basis of R square with respect to which the matrix of the transformation is a diagonal matrix, then we call such matrices as a diagonalizable matrix or diagonalization of the operator. The given operator is said to be diagonalizable if there exists a basis of R square with respect to which the matrix of the transformation is a diagonal matrix. Then we say that the operator is diagonalizable, or the any other matrix A is diagonalizable. Means A is similar to diagonal matrix. If such a basis does not exist, then that won't give you a matrix of the transformation as a diagonal matrix. In such cases, the matrix is called as not diagonalizable. So this is the intuition behind diagonalization of matrices as well as similar matrices. Similar matrices represent the same transformation with respect to different bases, and diagonalization of matrices or diagonalizable matrices are nothing but there exists a basis of the given operator with respect to which the matrix of the transformation is diagonal. So that's where the concept of change of basis has got the significance. Algebraically, when you have P inverse A P equal to B, then A and B are similar. If you have P inverse A P equal to a diagonal matrix, then A and B D are similar. Similar means it is similar to a diagonal matrix. Hence, your matrix A can be diagonalizable, due to which the linear operator also diagonalizable. So this is what the outline about the concept of a matrix of change of basis, which plays a very important role under the concepts like similar matrices and diagonalization of matrices. I hope you understood. If you like my videos, please share and subscribe to my channel. Thank you for watching.